Hiya! So in this video, we're going to start looking at the proof of Euler's rotation theorem and how it kind of goes about and how it works. Remember, we're probably not going to, So let's look at the identity. One thing we're going to do quickly before we do that is we're going to look at a remark, 1.79, which looks at the identity operator, I. So this leaves everything fixed. So I of x is equal to x for all x. Now this, you will notice, is a linear operator that's orthogonal and it preserves orientation. But if you think about this, if it leaves everything as is, it's not really rotating everything. It's staying exactly as is, right? And this is reflected by Euler's theorem, right? In essence, what this is happening is that the angle is 0, right? There's no rotation. And so what is the axis of rotation? Well, in particular, since I of x is equal to x, every vector is an eigenvector with eigenvalue 1. And so every line in E3 could be considered an axis of rotation. Another thing is to note that the trace of I is equal to 3, right? 1 plus 1 plus 1. And if we recall, this is also equal to 1 plus 2 cosine of phi. And here we saw that phi is equal to 0 degrees, right? So phi is 0. So this is another way to kind of see that the angle is 0. Okay. Now let's start looking at the proof. So the proof we're going to do in two parts. We'll see if this is going to be 2 videos or just 1 video, depending on how long this takes. But we're going to break this down. First, we have to show that there exists some axis that stays fixed. And the second thing we want to show is that P rotates the other 2 vectors around that axis. So in essence, we're first finding where the fixed line is, and then we're going to try to rotate around this. And this is what we're going to do. So first off, what we start off with is the following. That we start off with some linear operator P, and we want it to be an orientation preserving orthogonal operator of E3. And then we're going to have, what we're going to show is that there exists an axis L that keeps P of x equal to x for all x. So in other words, we're showing the existence of an axis of rotation if P is an orientation preserving orthogonal operator. So let's break this down. The proof. So here, we know that the eigenvalue is 1, right? Or no, we know that if P has an eigenvalue of 1, right? If this is true, if P has an eigenvalue of 1, then L is the one-dimensional space of eigenvectors with eigenvalue 1. In other words, P of x is equal to x. This is just the definition, right? And this is precisely what we want to show. Therefore, this gives axis of rotation. So we just need to show that P has an eigenvalue of 1. Okay, so how do we find the eigenvalue? This is the eigenvalue lambda is determined, has an eigenvalue lambda if and only if the determinant of lambda I minus P is equal to 0. Now, if you kind of go back in the day and you try to recall, okay, what is this? This, recall, is called the characteristic polynomial. So you can look this up if you don't recall what this is. In essence, you just want to solve this equation. And you want to show that lambda, that this has to be equal to 0. I is the identity operator, and lambda we want to show is equal to 1. So at this point, we just need to show, well, okay, let's make lambda equal to 1. And we need to show that the determinant of I minus P, sorry, this is what we want to show, so I'll do it in pink. We want to show that the determinant of I minus P is equal to 0, right? Because then that means lambda is equal to 1, and lambda is an eigenvalue of 1. Implies lambda equal 1. And here we're going to use properties from determinants that we've already seen a couple weeks back. This is things that you should kind of already have noticed a while ago. So first off, since P preserves orientation, we can just multiply by the determinant without a problem, right? This is not too big of a deal. The determinant is equal to its opposite, right? This again is not too big to a problem. Now we can put these together and multiply the matrices. And so we have P to the T, PT minus P. So here we multiply them together. Now this PTP part is equal to I, giving me I. And this is because P is orthogonal, right? I is equal to its own transpose, so I can flip this around. Now, a second characteristic is this one, that the sum of the determinants kind of stay, or the sum of the matrices stays the same. In other words, I can just pull this transpose out, so I get P minus 1 to the transpose. And then I'm left with that I can remove this transpose, I get determinant of P minus I. And this is just a minus of determinant of I minus P. So in particular, what we end up having is the determinant of I minus P is equal to the minus of determinant of I minus P. Now, in the real numbers, the only time this happens is when the determinant is equal to 0. So therefore, the determinant is 0, the eigenvalue is 1, and we're happy. And here, notice how we use both orthogonality and preservation of orientation, right? So we used preserves orientation here, and we used orthogonality here. So we do need both of those conditions in order to show this. All right, so we have an axis of rotation. We're happy. Now we're going to look at the angle. How do we figure out the angle? So that's what lemma 181 is about. So how do we figure out this angle? It's saying that if I start off with P, an orientation preserving orthogonal operator that fixes an axis L, the previous lemma says this L must exist, right? We look at the eigenvector whose eigenvalue is 1. Then P is a rotation about axis L by some angle phi. So that's what we're going to show. So let's look at this. I forgot to note this down. There we go. So first we're going to pick a unit vector n in L and pick an arbitrary orthonormal basis, right? I don't care what orthonormal basis it is. Choose your favorite orthonormal basis. And we're good to go. Here we're requiring that n be a unit vector, right? In L, so it has to be, so if we look at our line, it's got to be contained in this line. And here in particular, we're always forcing n to be the first element in this basis vector, right? This is going to force us, this is going to let us see that matrix we had seen a couple videos back, with the 1 in the corner and the cosine sine phi blah 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 on the bottom right hand side. Now, the previous lemma, since we have this line, right? We have this line of the eigenvectors. So this L is the line of eigenvectors. Line of eigenvectors. We know with eigenvalue 1, with eigenvalue 1, we know that P of n hat has to equal n hat. Now we want to first show the following. In particular, what we're really trying to show is that there's no component in n hat. So let's do it for F first, and it'll be almost identical for G. So we're going to do one at a time. So let's look at F. So here F I've let equal to mu n plus alpha F plus gamma G. And we're going to look at the inner products. So here we have the inner product. And so let's look at this. So here we can replace this one here. And then P of n, well, this is just equal to itself, right? Nothing changes. Now, by properties of inner product, I can pull these out, right? So this is n, this is f, right? So this is okay. Now, what do I know? What I know is that, where's my letters? This is equal to 0 because it's orthonormal. They're orthogonal. This is equal to 0 as well. This is equal to 1. And so we're left with mu. So in other words, the inner product of P of f and P of n give me mu. But we know that P is orthogonal, right? Since P is orthogonal, we also have the case that P of f, I don't want to go this far, that P of f and P of n, the inner product of these two, is equal to f and n, like the inner product of f and n. So I can kind of get rid of the linear operator. We had kind of seen this, right? This is the definition of it being orthogonal. And this latter half, right, this is orthonormal, right? By orthonormal basis, orthonormal, we know this is equal to 0. This implies that mu is equal to 0. And in other words, P of f has no n component. Easy. Well, relatively. It was a little bit of work. P of g we do in the same way, and we're left with the following matrix. So we have 1, 0, 0, 0, 0, 0, alpha, beta, 0, gamma, delta. Now, this matrix is orthogonal and orientation preserving. Now, we can repeat the calculations in 1.2 and 1.22. This was from, where was this? This was from last week in 2 dimensions. So we're not going to go over this, but this is from last week. And in essence, if we look at these kind of calculations and we look at P of f and P of g, then we're going to be left with these 2 formulas. And therefore, P is the rotation about the axis L by a phi. And that's it. So we'll stop this video here. It's way too long anyway. So we'll stop it here. And in the next video, we're going to talk about area, volume, and determinant. So I will see you then.